Good morning, kids. We'll discuss today the total internal reflection. The topic name will be total internal reflection. This will be our topic name, total internal reflection. Okay, now what is the total internal? We'll see like this. If a ray of light, let this be the incident ray. So here, let this be the angle of incidence. This is the boundary, so let this be the radar medium. Mu r. Let this be the denser medium. Mu d, and this will be the normal, and this will be, we'll call this as a boundary boundary or an interface. So the ray of light, now it is moving from denser medium to rarer medium. Definitely the ray will undergo refraction. It will bend away from normal. This is a typical path. Agreed? So now after refraction, the ray will bend like this. And this will be the angle of refraction. This is the angle of incidence. So what is the angle of incidence? This is the angle of incidence. Angle of refraction, this is the angle of refraction. As the ray is moving from denser to rarer, it will bend away from normal. You can check it. It is bending away from normal. Okay, now, what is the Snell's law? The Snell's law says that sine mu d sine I equal to mu r sine r. As I increases, proportional what happen? R must increase. As I increases, as this angle increases, definitely the R has to increase. From the sense now. Now I'll increase the angle of incidence. Then for one specific angle, the refracted ray, which is here, no, as the angle of refraction increases, for one specific angle of incidence, the refracted ray will graze the boundary. This condition will represent here the refracted ray. This is the refracted ray we have chosen. Some other color, let me choose here. The refracted ray will graze the boundary. You can check it here. So the angle at which the refracted ray grazes boundary, that will call that as critical angle. So then we'll apply the Snell's law. Here refracted ray grazes boundary. Then mu d sine c equal to mu r sine 90 degree, or sine of critical angle is equal to mu r by mu d. Then if I further increase the angle of incidence, the ray will get totally internally reflected. No further, the ray, what will happen, the ray will get internally reflected. All the energy will be reflected back. This condition is what we'll call as a TIR, or in short, we'll call this as TI, total internal reflection. All the energy will be reflected back. The total energy of the system will be reflected back. Then what is the condition for TI? The angle of incidence this particular thing, this angle of incidence, if it is greater than or equal to critical angle, the ray will undergo total internal reflection. So here after we'll write here for TIR, the angle of must be greater than or equal to critical angle. Okay, like this, there's a basic idea of the, so when do we see the TIR? Only when the ray moves from, this denser medium to rarer medium. We'll see this TIR. Agreed? Huh? No, if the rarer medium is air, we'll analyze next condition. If the rarer medium is air, if this is a rarer medium, if this rarer medium is air, the denser medium, let it be glass. Then we can define the critical angle. The critical angle for glass, we can define like this. So this is the critical angle. So what is the value of critical angle? This will become equal to mu g sine c is equal to refractiveness of air is mu air into sine 90. Mu g sine c. We'll write here critical angle for glass. This should be equal to 1 into 1. Like this, we can define critical angle for a pair of a medium. The critical angle will be defined for a pair of medium. What is the pair of medium here now? Glass and air. Similarly, we can define the critical angle for some different medium. So that what is the different medium? Let me choose glass and water. So what is the critical angle? Critical angle here will be call C, then mu G, and let this be mu W. This is the incident ray. This is a refracted ray. Now, how the ray is moving from the glass will graze the boundary and it will finally be moving like this. This angle will be 90 degree. Then, okay, they will indicate this angle. This will be 90 degree. So what is the critical angle for glass water interface? This should be equal to mu G sine C is equal to mu W sine 90 degree. So critical angle for this will be mu W by mu G. Like this, for a pair of medium, we can define a critical angle of a system. Now, similarly, if a ray of light, let this be the boundary. Let this be the interface. So it can happen that for a grazing incidence, there's a denser medium, there's a rarer medium. For look at the what is angle? This is the angle of incidence. So then this will be critical angle. This is incident ray. This will be now refracted ray. Then what is the condition now? Mu1, mu2. So we can write here, or mu r, you write it. Mu r sine 90 degree is equal to mu d sine of critical angle. The same thing. So for grazing incidence, means this is a boundary, no? This is the boundary. This everything is a boundary. If a incident ray grazes boundary, then the refracted ray will emerge at an angle, critical angle with respect to normal. This will be the normal. We'll call this as normal. Sir, how come if it is grazing, then what makes it to like a deviate here? It can proceed further straight like this. This is a typical question what many will ask here. Means if a ray is incident, grazing incidence, then we should continue to move. No? We should proceed further. What makes it to deviate like this? In fact, here it is not like angle of incidence 90 degree. The angle of incidence will be slightly less than 90 degree. The angle of incidence will be around 89.99 degree, but not 90 degree. Then definitely 89.99 approximately we can put it as 90 degree. There's a main idea of this one. So this idea will be using exclusively in the prisms. Huh? You have to grazing incidence, grazing emergence. So what is the basic condition for a for a ray to undergo TIR? The angle of incidence must be greater than or equal to critical angle. This is one basic necessity condition. And when do this TIR will take place? Only when the ray moves from denser to rarer. Okay, fine. So in coming class, we'll discuss the next concept. Thank you, all of you.
On the surface of transparent homogeneous liquid. The source disappears. I think it's asking some TIR ideas. Nothing is big is there. So there's a disk is there. We'll go for plane diagram. Below everything is there's a liquid. Now when the height of the liquid is something say 1.33 centimeter, the rays what happen will undergo TIR or they'll graze. And no longer they'll undergo refraction. I think so. This should be what? This should be the critical angle. And there's a radius R. It's there in S.A. Verma. As the level falls, when the level of liquid is something is equal to H, the ray what happen will undergo TIR. I'll make. Get into this one. So there's a liquid. So critical angle. So what is a mu? Mu is equal to sine c is equal to 1 into sine 90 because this is air. So this is a disk. So we got the value of sine c. What is sine c? Sine c should be equal to. So first what we have a triangle. Tan c is equal to r by h. From this you calculate the sine c. Substitute that. So mu r by root of r square plus h square equal to 1. Substitute r and h value. So you'll get the required value of mu. What is the basically concept as the silica as the level of liquid increases, then the angle of incidence will decrease. Then when the angle of incidence becomes less than critical angle, the ray will undergo refraction. So that the person is able to see. So now the person is unable to, no rays will enter the person's eye. Please understand the very small some idea is involved here, nothing big. When the level of liquid is more than H, the ray here will undergo, when the height of the liquid is more than H, the rays here will undergo refraction, and they will enter into and is able to see. So once what happen, when the height of the liquid becomes less than or equal to this, what happen, the rays here will be incident at an angle of incidence equal to critical angle. So the ray will undergo grazing ray emergence. And because of that, what happen, the rays will not enter into eye and is unable to see the bottom. I should show it here. Huh? So actually what happened is like a somewhere here. So here, that's okay. Somebody is asking, sir, what is the source? Source is here which will emit light. Or don't think like this, sir. Here high is there, so this will block. So that this light, what will happen, will enter. Only when it undergoes totally. What about this ray? It will undergo TIR, no? So there's no doubt on that one. No? What about this ray? It will undergo TIR. I'll draw the diagram. Meanwhile, you think it. Huh? There's a thing. Okay, here. So it's telling the ray is incident at 45 degrees. So the ray, what will happen, move from rare to denser medium. So should bend towards normal. Take like this diagram. So it should undergo here. If it undergoes TIR, just undergoes TIR or let it be this one. So this is the ray is incident, double ear refraction. Here it will undergo TIR. So here the ray enters at A. At B should undergo TIR. Then only it cannot emerge from this particular side P1 or P1 P2. I discussed in class. So once again, I just wanted to revise it. So what is the basic condition? R plus I should be 90 degrees and the angle of incidence here. This I should be, what should be the angle of incidence here? This one should be greater than or equal to critical angle or should be less than that one for it to undergo. So there's a normal, this AB ray AB will become an incident ray and this will become angle of incidence. If angle of incidence is greater than or equal to critical angle, the ray will undergo TIR. So first, what is the basic necessity condition? I must be greater than or equal to critical angle at B for the ray not to emerge from P1, P2. So let's get into so here I plus R should be 90. So I replace I, this will be 90 minus R. Applying Snell's law on both sides. Sine of 90 minus R. Shall we go for cos R? Then applying Snell's law at A. Okay, I'll verify it. Huh? This one, so sine 45 equal to, this is mu, no? Mu sine R. So this will be 1 by root 2 mu sine R. So cos R has to be replaced. So for that, we have 1 by mu root 2 equal to sine r. Cos r will become root of 1 minus sine square r. Sine 3 should be 1 by mu. 1 minus sine square r will be 1 by mu root 2 whole square greater than 1 by mu. Substituting this, 2 mu 2 mu minus 1 mu square, no? Mu square.
There it should be root 2, sir.
Which one?
First one. The denominator.
Okay, that one. Mu root 2 mu 2 mu square. Correct, no? It will be like a 1 by
First expression on the right side, sir.
root 2 whole square. Okay. Yeah, there should be root 2. Okay, I think I messed up here. 2 mu square will come 2 mu square minus 1 mu square root 2 will come outside. Mu square get cancelled, so here root 2 will be there. Okay, fine. Yeah, this will be root 2. Squaring this will get only 2 mu square minus 1. Yeah. What is the idea? The minimum value of refractive index. If mu is greater than root 3 by 2 for any angle or only for 45 degree, this is applicable. Okay, finally we got answered. So how to interpret that one? Only for angle 45 degree, this is applicable. Or for any angle of incidence. I think in class I discussed for any angle of incidence, what is the minimum value of mu so that it will not escape from you. What we brought is for 45 degrees. Anything greater than this, it will undergo TIR. So for any angle of incidence means again we have to bring that condition. In notes there, just verify that one. There's a difference between those two ideas. Are there. In class for any angle of incidence, the ray must not escape from P1, P2. That was in class I discussed. And it was mu equal to root 2, greater than or equal to root 2 it was. Here some at angle 45 degree, the condition is brought. Just do make observation what conditions that are made available. Similarly, one more. And there's a fiber optic cable. Even in advance, they may ask you regarding the fiber optic cable. This, if you want, you can write this as a cable. No? As a refractive index 4 by 3, it is surrounded by a medium of refractiveness 2. A light ray is incident at the midpoint of one of the rod, as shown in figure. The incident angle theta for which the light ray grazes along the wall of the rod. The same numerical date was theta 45 degree. Here the theta is unknown. The theta is what is asking. The mu of the cylinder and mu outside given. Please do things. So what is available? The mu of slant. What is this angle of incidence was given? This is here. Okay, okay, get this one. So this is a, so he was asking the value of mu. So what is given now? Mu of this medium, mu of the slab. He's asking what is this angle. I think both are same questions. Only the diagram little bit conditions are changing here. So the ray what happened must undergo TIR. This is theta. So the ray is moving from, okay, this is a mu1. I'll write it mu2. And the ray is moving from right to 4 by rho 3. Denser to NO should bend away from normal. Mm-hmm. 4 by root 3, 1.7. Okay, the right to denser. So it should bend towards normal. So here the ray should undergo, so it should graze this one. Okay, start like this now. This is theta. Call this is say some r. Okay, this is phi. Then r plus phi should be 90. There's one basic condition. Then this phi should be equal to critical angle. And we have refractive index mu1. So what is the basic Snell's law of refraction? What you apply here? Mu2 sine phi should be equal to mu1 sine 90 degrees. So mu2 is how much? 4 by root 3 sine phi should be equal to mu1 is 2 into 1. So sine phi is equal to root 3 by 2. So this angle now we know it. How much it is? 60 degrees. Then what is R? R will be 30 degrees. Directly come for this one. What is sine theta? So mu1 sine theta should be equal to mu2 sine R. Mu1 is how much? 2 sine theta. Mu2 is 4 by root 3. Sine R will be 1 by 2. No need of any much mathematics. Straight away you have to apply this condition. I think these are very important. You check advance. Something related to TIR 7 times they've asked and not 1, 2. So we think that something very good maths-based problems, that one. But the TIR is what he has asked 7 times. Huh? Different cases of TIR is what I'm just bringing. So in with Prism, more TIR applications are there in Prism. Go through some TIR. Definitely, the ideas involved will be very not troublesome. No, just applying the Snell's law condition. Nothing big there. But he has asked us 7 times, not 1, 2. Please give priority for such small topics which doesn't need much mathematics here. This can be fiber optic cable also. If I make angle, if I increase theta, what will happen to R? R will increase. R will increase. If R increases, phi will decrease. Then it will escape. So therefore, so what should be the angle of incidence? If I make the angle of incidence here less than theta, so if I further decrease, R will decrease, this will increase, and this is the critical angle. No? If the angle of incidence more than critical angle, then it will undergo TIR. So this is called like a launching cone angle. So if you draw a cone here, so any ray which lies within that cone, it will undergo successive TIRs. So after this, what happens? If I just make the angle of incidence here less than theta, here the angle of incidence will be greater than critical angle. Then the ray will undergo TIR. Successive TIRs it will undergo, and it's going to reach the one end to another end without loss of light. Let me just cover that concept here. No, there's a ray of light. If this angle is what is the length even if this length is of 1,000, 100, 1,000 kilometer, no, it is going to undergo TI. So what is this angle? This alpha should be less than theta. It will undergo successive TIs. You need not to bother. It will continue. I'll extend further a little bit. Any conceptual question can be asked if they're in advance. Let me move this. It will undergo successive TIs. How many? Like as long as the length of the tube is there, no, length of that particular rod is there, it will undergo successive TIs. Okay, please do remember any general passages can also be asked in final advance, so you have to be careful. Provided that alpha should be less than theta. Okay, we have one more.